Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, good afternoon everyone. I'm very happy to have Andrea Montanari from Stanford here. I feel some responsibility for Andrea being in the US, as when I was running a program in MSRI in Berkeley in 2005, he was a postdoc in the program, and people in Stanford saw him, and the rest is history. So I'm always amazed by the variety of and depth of results that Andrea obtains, and he'll tell us today about large matrices beyond singular value decomposition.
Okay, thanks, Yuval, for the introduction and the invitation. Yeah, so what I try to do is review a bunch of things that us and other people have been working on in the last couple of years. Okay, so this doesn't work. Oh. Okay, so I'll start with two kind of motivating examples. One is graph localization. What is this? You have a cloud of points in a low-dimensional space, say in the plane, and you want to find the points positions from some measurements. Okay, and this has a number of applications. One is manifold learning and dimensionality reduction. One is positioning. There is applications in NMR spectroscopy. But to have in mind a simple model, here is a simple model. You have the unit square in the plane, and you throw n random points uniformly and independently in the plane. Okay? And now the question, okay, so what you measure is that you measure the distances between pair of points if the pair of points are closer than a certain range. Okay? So in this case, I took all the pair of points that are closer than something like that, and I connected by an edge, and I measured the length of all these edges. Okay? And I measured them not exactly, but with some error. So I get this matrix of measurements, d tilde. And now the question is to make sense of this big matrix of measurements. In particular, can you find the point positions? How accurately can you find the point positions? How quickly can you do it, etc. Okay, so this is one case in which data came as a matrix, and there is an underlying low-rank structure that comes from the dimensional, low dimension of the geometry. Okay. Second example is collaborative filtering. Here you have a big matrix. This contains ratings given by a bunch of users to a bunch of, say, movies. And the matrix is very sparsely populated in the sense that the ratings only, each user only watched a very small subset of movies. Okay, and just to make things concrete, these are the numbers that came up in the Netflix challenge. You had 500,000 users, 20,000 movies, and about 1% of the entries were revealed. These are numbers between 1 and 5, and tell us, for instance, how much did Yuval like, I don't know, The Devils Wear Prada. Okay, and then with it came a bunch of queries, that is question marks, asking us how much will Yuval like, I don't know, The Lord of the Rings. Okay, and, so people were challenged to predict these missing ratings with a root mean square error below 0.8563. Okay, and you can try to win the challenge. I actually tried for a couple of weeks. I thought it was easy. But then decided that it was very hard. And even the question of, can we make sense of this? For instance, people spent 3 years trying to beat these numbers, and eventually they beat them. How did they pick this number? I mean, what is the reasonable precision that one can hope to achieve? Okay, so I start by describing a model for which is okay model for the last problems, an algorithm and some analysis, some numerical experiment, and then I switch to this graph localization, and then some result on this. Okay, so what is a model then? This, of course, if you want to predict the rating, the entries of this matrix, this is a huge matrix. You have 1% of the entries. If you want to say something at the entries that are missing, you need some structure. So what people do in this field is normally they assume that one common model is that the matrix is actually low rank or approximately low rank. So let's think that there is an underlying matrix of actual ratings that has rank R. So this is U sigma V transpose. And our model will be that to it we add the perturbation Z. And then out of this N matrix, this noisy matrix, we observe a sample, and the sample is a uniformly random sample, okay, of some size. Okay? So you can think this in two ways. Either you observe each entry with some probability, or you observe a uniformly random subset of entry of a given size. These are essentially equivalent. Okay? And this is the sample here. Okay, so I will indicate the sample as NE. So this is the matrix where I put to 0 all the entries that I didn't observe, or I put to a reference value. And now the objective, well, this is very, very clearly said in the Netflix challenge, is to get an estimate of the whole matrix that minimizes this metric. This is the root mean square error. So it's the sum over all the entries of your prediction minus the actual value square root of. Okay? So this is just normalized Frobenius distance between M and M hat. Yeah.
So where does the matrix have a low rank in the Netflix challenge?
Okay, so I'll show you actually the singular value decomposition of this matrix in a few slides, and you can see that there are some big singular values. So it's not too a bad hypothesis. As a matter of fact, people that won the challenge, a big part of their method was having this kind of model in it. There is an end-waving justification that I don't know how much you should believe, but is that every person can be characterized by a low-dimensional vector, every movie can be characterized by a low-dimensional vector, and then the rating is just the scalar product of these two vectors. Okay, but it's a good question. So the parameter of the problem are the data size is M by N, the rank R, and the sample size E, modulus of E. So I think E as a set, and this is the size of the set. And then this noise matrix, I call it noise, but one should think it as whatever is not explained by the low rank model. Right? And actually, as a running example, we'll use this example that it's very friendly. It's IID noise. Okay. Okay, so some background. So what I want to understand is the trade-off between these things. In particular, how many entries do I need to learn a certain matrix of given R of a certain rank R within some accuracy. Okay. So a little bit before we started working on this, or while we started, Emmanuel Candes and Benjamin Recht came up with this very nice condition on the matrix. So they looked at classes of matrices that satisfies this incoherence condition. So U and V are the factors. Okay, so these are skinny matrices, and this condition is telling you that the average norm of any rows of this is 1. And this condition is telling you that the L2 norm of any is R actually, and the L2 norm of a row is not much larger than the average L2 norm. Okay? The average L2 norm is R. The maximum L2 norm is not much larger than that. Another way of saying this is that if you look at this matrix, these factors, these are not aligned with the coordinate axis. Okay? So this is a condition. And they proved under this hypothesis that if this matrix M satisfies this condition, then you can learn it from n to the 6 over 5 times R entries times log n. And so you can learn in the sense that it's uniquely determined by the observed entries, and it's the unique minimum of a semi-definite program that is very easy to write. So here I'm thinking, for simplicity, of the case in which you have no noise. So the matrix is really rank, say, 5. And they are telling you that 5 times n to the 6 over 5 is sufficient. Okay?
The condition was about the matrices U and V that were
right. Yeah, so the condition is about the factors, saying that the factors are not aligned with the coordinate axis. The reason why you need this condition to learn exactly, you understand very easily, is if you think of the following low rank matrix, rank 1 matrix. Take the matrix that has 1 at entry 1, 1, and 0 everywhere else. Unless you pick the entry 1, 1, you will never learn it. Okay? So if you want exact reconstruction, you need something like this condition. Okay? And if you need exact reconstruction, there is a lower bound. Right? So this is a nice result. Okay, the SDP was actually introduced in this paper by Marianne Fazel, that was a student in Stanford. Okay? So it's a great result. It's a couple of inconvenience. First of all, if you think of how well can I hope to do, the number of degrees of freedom in such a matrix is of order rank times n, right? Because I need just 2 rank times n, right? And here you are requiring me to give you n rank times n to the 6 over 5. So this means n to the 1/5 observation for each, say, bit of information. Okay? So this can be made precise. Actually, there is a lower bound that is r times n times log n. And this upper bound is n to the 1 over 5 above the upper bound, the lower bound. Second, this was only for the noiseless case, and I'm very well satisfied with root mean square error, say 0.8. And finally, this proposes a semi-definite program, but the complexity of semi-definite programming, it's a polynomial, but it's a decent polynomial, n to the 4th, and you're interested in solving it for huge matrices, and this can be done only for matrices that are 100 by 100. Okay, so now I'll try to do something. I don't know if I'll succeed in it, because, okay. Oh, I didn't succeed in it. Okay, too bad. I realized just a few hours ago that this wasn't working. It used to work. Okay, so this was supposed to show how, this is a big matrix. It's actually a matrix that is few thousand by few thousand. And this is the error between the reconstruction and the actual matrix in color coded. Red means big error, white means small error. And supposedly we should have a movie showing that as you reveal more and more entries, you actually are able to reconstruct it.
Restart the browser.
Sorry? Oh, wow. But then I have to point it. Restart it from scratch. Okay. Yeah. Okay. It's a pity. It was a fun movie. I can. It used to work on. Sorry? 5. So what's very nice, I can mimic it for you, what you will see in this movie. So you see this red-white stuff that floats around, and then you reveal entries that are little blue spots. And then at a certain point, all the red goes away, okay, very rapidly. Okay, meaning that you cross a certain number of entries that you revealed, and the error in reconstruction very sharply goes down. If you plot it, actually the error in reconstruction is approximately constant until a constant times n times r entries, and then it goes down exponentially. So each entry that you reveal goes down very rapidly. Okay. Okay, so let's stop with the fun and talk about the mathematics. So what is a naive approach? A very naive approach for trying to reconstruct this matrix is just using some spectral method. Okay, what is the simplest thing? You take the matrix in which you put to 0 all the entries that you didn't observe. So this is NE. You compute the singular value decomposition. Okay, so are the singular values. And then you pick you retain only the largest R singular vectors and singular values and set to 0 all the rest. And you have to rescale this by some factor in such a way that this in expectation is the real matrix. You know, if you eliminated most of the entries from your thing, you decrease the overall norm. So you have to boost it up exactly by, this is 1 over p, 1 over the probability that each entry is sampled. Okay? So this is just projecting, finding the rank R matrix that is essentially closest in Frobenius norm to your observation. Okay? So this naive approach fails if the number of entries is very small, if the number of entries is of order n. Why? Well, because if you think of your matrix, call the degree of a row the number of entries that are revealed in the row, there will be some rows that have degree log n over log n. This is the extremal of a Poisson. And corresponding to these rows, there are singular values that are of order square root of degree. So square root of log n over log n. So this is like if you take a random G and P graph with p equal constant over n, the largest eigenvalue will be of order square root of log n over log n, and it's completely concentrated on the highest degree node. It's not something that really faithful. Okay, so we have to take care of this. So there is actually a easy trick for this. Every time I see a row or a column that has twice the expected number of entries, I just trim it. So I identify it and I throw away all those entries. This is a bit of funny and it's a bit harsh because I'm throwing away data, but it's good enough for proving theorems. In reality, you could do better things than this, but this is good enough. So this is the naive algorithm. It's not going to be whole, but the first part of the algorithm is just take n, I trim it, so I set to 0 the non-observed entry, I trim it, and then I compute the rank R projection. And what is true for this is that the root mean square error that you achieve is what? Is the sum of two terms. One term is the error that you would make without noise. So this is this correct behavior as the size of the right, the maximum entry, times square root of the number of degrees of freedom times the divided by the number of observation. And then as a term that has to do with the noise. Okay? And what matters in the noise here is the operator norm of the noise, of the observed noise. So just the sparsified noise matrix. These two terms are roughly of the same size in my running example. Okay? So this is actually not something that people just started looking at. Computing this singular value decomposition is something that has been going on for a while. So this is, for instance, a nice theorem by Dimitri and Frank Mescherry. So here the motivation was a bit different, was having fast linear algebra algorithms. They proved the following, that if the number of entries is n 8 log n to the fourth, then the error, this is in the noiseless case, is of the same type as we proved there. Okay? So this is essentially the same theorem except for this 8 log n to the fourth. Now, since Dimitri is here, I want to provoke him. So he will tell you that 8 log n to the fourth is not a big deal. What are a few logs between friends? But if n is 10 to the 6, which is a good number, 8 log n to the fourth is bigger than n. Right? So, okay. All right, but this is essentially the same theorem. So we just are a bit more carefully about proving it. No, it's not that he's not careful.
Because you had the advantage that you could look at his theorem.
Yeah, that's what I wanted to emphasize. So this is how it looks on a random matrix. You see, if you take a random rank 4 matrix and then you sparsify it, you will see 4 big eigenvalues and then a continuum of eigenvalues. The precise spectrum here is this is how it looks real, the Netflix matrix. Unfortunately, the picture is not as nice as before. You don't have this nice gap between big eigenvalues and small eigenvalues, singular values and smaller singular values. Okay. So now this is not the whole algorithm. What we do is that we do that, and then we take the root mean square error and try to minimize it greedily. This is nothing sparse. I will not be precise about what I mean by minimizing greedily, if you want, but we do some sort of just gradient descent to minimize the root mean square error, starting with this factorization. And precisely the cost.
Actually, can you just show the graph one more time? So how many spikes you have to consider for net each data?
So typically people do between 20, 50, things like this. Okay? So 20 gives already 0.91 something. The objective was 0.85, and the baseline is 0.95. Okay, so you minimize greatly what you are minimizing it, the error on the observed entry. So this is sum over all observed entries of the real value of the matrix. Okay, this should be n minus your conjecture singular value decomposition, and you just try to minimize it by some coordinate descent. So what we prove here, so this is the theorem before. Okay. Now, if you take, what we prove here is that we take an incoherent matrix. It has to have a bounded condition number. So this is the ratio of the largest singular value to the smallest singular value. And the number of observed entries, that is a constant times n times r times log n. And then there is a small overhead that shouldn't be here. This is the minimum of r and log n. So think of this as log n squared. Then this algorithm that I described achieved root mean square error, that is this thing. So this is just, if you look at it, it's just this term in the original thing. So the singular value decomposition has the sum of two error terms, one that is due to subsampling and one that is due to noise, or to non-rank R part. Okay. Now this part has disappeared. After you do this minimization, you get this thing. Right? So you are left only with this contribution. Right? And the complexity, so the original theorem, we didn't have any bound on the complexity, and we didn't have this. So we had this worst sampling condition. And now we have a paper that we are about to finish where we have a bound on the complexity, okay, on the number of iterations. So this is linear, essentially linear in the dimension, and cubic in the number in the rank. Again, for my nice, running example with IID noise, this, if you evaluate this operator norm, this is essentially square root of Rn divided by the number. So it's the right behavior that you should have. So this is the number of degrees of freedom divided by the number of observation. So there are kind of two interesting things about this phenomenon, okay, that we and other people. First thing is, singular value decomposition is really a cornerstone of solving many of these problems, and this has been studied in great detail. And now the nice thing is that you can do much better than it, qualitatively better. Not for all matrices, but for some good class of matrices. And this is something that practitioners knew for a while, people in machine learning, in the sense of running this type of greedy algorithms. But now we are starting to understand a bit more of it. And what is the difference really is that, what is singular value decomposition? You minimize the Frobenius distance of your observed matrix minus a rank R matrix. Now what I minimize is the Frobenius norm of the projection on the observed entries of the difference between these two. Okay? So PE is just the operator that takes a matrix and sparsify it by setting to 0 all the entries that you don't observe. So the distance difference between this and this is that this can be solved in closed form, essentially, by singular value decomposition. This cannot be solved in closed form. On the other hand, if you think of what you should do this, right? Because here you are downweighting entries that you don't observe, while here I'm just penalizing the error on the entries that I observe. Okay? And the second surprise is that somehow the error in singular value decomposition is sum of a noise term plus a sampling term. Here you have noise divided by sampling factor. Okay? Okay. So we have not been the only one who have proved this kind of theorem. So there is, after doing the exact reconstruction, Candes and Recht, then Manuel Candes and Terence Tao strengthened the same result, and then Candes and Plan looked at the noisy case. So if you put these two, Candes and Tao, Candes and Plan together, you get this kind of result. If the matrix is strongly incoherent, so I will not explain what this is just an hypothesis that is stronger than incoherence, but they don't have any assumption on condition number, and the number of observed entries C times R times N times log n to the 6. Okay? Then the semi-definite programming achieves this error bound. Again, if there is no noise, this means exact reconstruction. If Z is 0, this is exact reconstruction. If Z is non-zero, then you have some errors. And the difference is that the error here scales like the Frobenius norm of the noise matrix, while in our bound scales like the operator norm. Okay? So between the two, there is a factor square root of n, and the square root of n shows up here and here. Okay? And there has been in the last couple of years, many papers coming up about the same topic. There has been a beautiful couple of papers by David Gross and co-workers. So this Rn log n to the 6 was in this Candes and Tao. It's really 40 pages of moment calculations. It's really scary. So David Gross realized that you can achieve a tighter result if you use these very nice martingale inequalities for sum of IID random matrices. There is Bernstein inequalities tells you something about the tail of the sum of IID random variables. There is an inequality by Alsvede and Winter that tells you about the norm of the sum of IID random matrices. Okay? It's beautifully, it's very powerful. Okay? And okay, these people, Martin and then Natis Rebro, looked at slightly different settings and have other bounds. Okay. Okay. Let's skip this, perhaps. So just a couple of numerical experiments. So this is okay. It's a case that is not particularly difficult, but still to show that a lot of algorithms have been proposed. These are matrices that are 1,000 by 1,000 of rank 10, and I generate them randomly. So what I do is just I take a factor that is 1,000 by 10, and this is IID Gaussian random variable. I take another factor like this, I take the outer product, I get a matrix 1,000 by 1,000, I sample here it and try to reconstruct it with various algorithms, and this is epsilon is the ratio of the number of revealed entries to the dimension. And you see that the probability of success is for all these algorithms a sharp kind of threshold phenomenon, and there is a lower bound that you can compute using rigidity theory. So this is Singer and co-workers in Princeton. So you get a lower bound, meaning that below this epsilon, for these few entries, you cannot reconstruct it. There are multiple solutions. Okay, so this is a group Goldfarb and Dada in Columbia. This is a group of people at UIUC. So these are various approximate methods to get the solution. This is our algorithm. So you can get fairly near for these random matrices. Right? And this is for a noisy example. So this is actually from this paper by Candace and Plan. This is a matrix 500 by 500 of rank 4. I add the IID noise with variance 1. And as you see, as the number of entries over n increases, the error goes down. There is a kind of oracle bound that you can compute. There is an obvious lower bound that you can compute as follows. You assume that one of the two factors has been given to you. Okay, and you'll just try to reconstruct the other factor. Now this becomes a least square problem, and you can tell pretty much everything about it. And this gives a lower bound. And okay, so this is our algorithm. This is what singular value decomposition does. Okay? So this is kind of nice because you see that singular value decomposition gets there at the ideal point where all the entries have been revealed. Okay, and as fewer and fewer entries are revealed, the two diverge. Okay, so this is really the gap that what you lose doing singular value decomposition. Okay, and this is, unfortunately, things are not as nice if you now you go back and try to solve the Netflix challenge. So these are three algorithms. Okay, the best one is this one. So the black one is the one for which we have a proof. And the other two, this is alternate minimization. What is the idea? You minimize the same cost function, but you minimize over x and over y, and then over x, and then over y, etc. This actually was first studied by a group at Microsoft in India. So you get this curve, and this is another algorithm that is better, for which we have no proof. So the prize was kind of here. We are not there. But one interesting thing is that this is the error on the entries that you didn't observe, and this is the error on the entries that you observe, right? So you see this gap is due to overfitting somehow. On the entries that you observe, you achieve a root mean square error that is smaller than the prediction error.
So does it make you do a non-unique reconstruction?
Sorry?
Does it make sense to make a non-unique reconstruction, some approximate?
Yeah. If you just want to come up with a matrix, you are not required to. If the matrix is not exactly rank R, now what is good or bad depends a lot on your metric, right? So you might.
Therefore, there must have been studies and do this kind of thing.
Sorry?
How does it compare with those kind of algorithms when you do this kind of reconstruction?
Yeah, I mean, I don't understand what it means, no unique reconstruction, really, right? So, I mean, you come up with a guess for each value of each entries, and now you can decide on the basis of that. This is your prediction. Okay, so I'll have one slide about proof. Okay. So again, the algorithm that I described is that you do the rank R projection by singular value decomposition, and then you minimize the cost function greedily, starting at whatever singular value decomposition gave you, and the cost function is, think of the noiseless case is UV transpose, this is your factor, minus XY transpose, this is what you're minimizing in, and you sum these over all the observed entries. So what is the strategy of this proof that we had? Is the following. First, you prove that the singular value decomposition is not too bad. Okay, so this is this first theorem, and this actually, the way we do it, we use this technique that people used in random graph theory. So this is originally dates back, I think, to Friedman, Kahn, Zemeretti, and Feigen and Hofeck. So what these people, Feigen and Hofeck, did is that they took a random G and P graph with P equal constant over N. They trimmed the high degree node, and they proved that once you trim the high degree nodes, the largest eigenvalue is bounded, is not square root of log N over N. Okay? And so now how you prove it, there are two ingredients. One is what you would do also for a dense matrix. That is kind of, you do a epsilon net over the unit ball, and then you tail. Okay, you look at the Rayleigh quotient, and then this is the maximum of the Rayleigh quotient is like the maximum of a process on the sphere, and so you have to bound the maximum of this process on the sphere. What is nice here is that okay, you have to deal with the fact that the graph is sparse, and here they do it using expansion. And essentially we extend this proof to rank R. And then what one has to prove is that once you are close enough, this cost function is nice in the sense that it's lower and upper bounded by a parabola, which has its unique minimum at the correct reconstruction. So it's locally convex somehow. The point is that this optimization problem is a non-convex problem, but in the neighborhood of this minimum is convex. So we prove this. Okay. Okay. So this,
the bound you have here do not yet imply convexity of the bounds.
Yeah. So locally convex was a sloppy way of saying it. We don't. So what we prove is this, and we prove is that the gradient doesn't have any zero inside that neighborhood. So the two things are sufficient to show that gradient descent converges to the minimum. Now, okay, this was the proof technique until 1 year ago. Now we have a better proof technique that actually, because this proof technique that doesn't give a good bounds on the number of iterations, now we have a better one that gives a bound on the number of iterations and uses this. Now that we learned this Alswede-Winter, now we use this Alswede-Winter inequality. Okay, so in the last 20 minutes, I want to talk about this graph localization. So there is the way I got into this graph localization is that I was thinking about this collaborative filtering model, and I thought that the model is somehow a big lie. Okay, the model that I studied has a big lie in it. Okay, and the big lie is that in the model each user rents a uniformly random movie. Okay, now earlier work just Dimitri a few days ago pointed to me that earlier work that used the singular value decomposition actually looks at a richer model in which entries revealed also depend on the value of the entry. But this is just for singular value decomposition, and also those kind of models have very strong assumptions, like the conditional distribution of observing an entry given the value. Okay? But here there is a big stumbling block. It's not true that you go to whatever Blockbuster, right, Netflix, and you pick a uniformly random movie out of it, right? At least I don't do it. Okay, so somehow this is a model that has the same feature. So what you would rent is probably movies that you expect to like a lot. So you expect to sample entries that are large. Okay, so you should think more of a matrix that is approximately low rank, and the subset of entries that you observe are those that are large. And so this is somehow similar. It's just something to think about. And it's simpler to think about. You have a point, and the entries that you observe, the distances, the pair distances that you observe, are those that are small. Okay, so it's very much related. Okay, and where is the underlying low rank structure? Well, suppose that I measure all the pair distances, the distances between all the pairs, and I measure them exactly, and I construct a square matrix that has the square of the distance between I and j at entry ij. So this is an n by n matrix that has entry ij as distance ij square. I claim that the rank of this, okay, there are too many d's in this slide, but the rank of this is the ambient dimension plus 2. Okay, so in my drawing is 2 plus 2. Okay, and this is just something that it's 1 minute. It's because this d is just dij is just xi square, which is rank 1, plus xj square, which is rank 1, minus 2xi xj, which is rank d. No? So you can think of this problem as essentially the same as before. You have a rank d plus 2, a rank 4 matrix on which I'm subsampling entries, and then I want to reconstruct the whole matrix. And now the interesting thing is that all papers on this topic start with saying graph localization is a nice application of these ideas, general ideas. But if you run any of the algorithms that I described before, they don't work. Just because of this fact, because of the entries that you are sampling are only the small entries. So of this matrix, you only observe those entries that are smaller than some range. Okay, so here is an algorithm that instead, let's say, kind of work. This is not the best I can program, but is what we analyzed so far. So the input is again these now perturbed distance measurements, and I want to come up with a set of low-dimensional coordinates that are accurate up to a rigid motion. Of course, I cannot identify points because rigid motion don't change distances. So I solve this SDP problem. I take a cube. This is a problem in the matrix Q that is an n by n matrix. I minimize the trace of Q subject to Q positive semi-definite and essentially a bunch of linear constraint of Q that tells me that Q reproduces the correct positions within an accuracy delta. And so I come back to this in a minute. Once I have the solution of this, I compute again the decomposition of this. This will be a symmetric matrix. I compute the eigenvalue decomposition of this. I take the largest d eigenvectors, and I give you back this as my embedding of the points. Okay?
So is there noise here, or there's no noise?
Yeah, there is noise. I'm assuming. So there is noise, and this is in the algorithm reflects in the fact that I'm not trying to reproduce the measurements exactly, detailed exactly, but I only try to reproduce them up to some accuracy delta. Okay?
So here the noise is not a probabilistic model, but the worst case.
Yeah. So okay. Well, so one thing at a time, one piece of notation. What is this Mij? This is just this Mij is just the matrix that has entry value. All entries 0 except entry II, which is 1, entry JJ, which is 1, entry IJ, entry JI, which are -1. Okay. Then when I compute, so if you think of this, so this is this semi-definite program that I try to solve. What is the rationale for this? So this is again the semi-definite program. Suppose that this is, you decompose it in this form. This is a positive semi-definite matrix, so you can always write it as x times x transpose, and therefore the entry ij is a vector xi dot vector xj. Now this thing is equivalent to minimize the trace, will be the sum over all the diagonals, so it's the sum of all the product xi, so the sum of the square of the positions, subject to, what is this constraint? If you write it down, it's just telling me that xi minus xj square is far from d tilde at most delta. Okay? So this Q, what this really is the gamma matrix of my points. Okay? And this, so this is the scalar product between matrices, the obvious, trace of AB transpose. And this scalar product is extracting me this object. Okay?
Why are you trying to minimize this trace?
Excellent. I'm trying to minimize because I need to minimize something. And second, because the problem is invariant under translation, right? So if I don't put anything, so ideally I would like just to find something that satisfies this. So if I can solve the feasibility problem, I'm fine. What this really does is that it centers the points, right? So it takes out the center of mass. So whatever solution you get will have center of mass at the origin. So in the end, in the proof doesn't play any role. Okay, so what is known? People looked at this SDP relaxation, mainly motivated by positioning. So and Ye and Bis was, so mainly Ye and co-workers. So they proved this kind of results that if the measurements are exact and the graph is a D+1 trilateration, then this algorithm returns the correct position. So what does it mean, D+1 trilateration? That there exists an ordering of the points, of the vertices, such that vertex I has at least the D+1 neighbors between 1 and I minus 1. Okay? Where does this come from? Imagine what is the simplest algorithm for finding positions. It's just triangulation. You first position 3 points, and then you find a 4th point that has 2 neighbors among the first 3, and then a 5th, a second. And so this theorem says that if the measurement exact and triangulation works, then SDP works. That is nice to know.
If you even need SDP, it seems like if you have no noise, it's a conditionally negative, it's called conditional negative definite matrix. You can center distance matrices and turn them back into graph matrices uniquely if there's no noise. So why can't you just...
But I don't observe all the entries.
So you're saying it doesn't, so that's only true if I have all the distances.
If you have all the distances, then you don't have the problem. So you have only subset. So if I have the subset, the simplest method is what, as usual, what Gauss did. It is just do triangulation. And but now people that do this kind of things, many application people complain about this because it's not robust. Right? For instance, I was reading that the way they first measure height of mountains of K2 and Himalaya was to triangulation, and for a while they were convinced that K2 was higher because along the way somebody got the wrong measurements, right? And then this propagates. So, but of course, this theorem doesn't show what is the advantage of doing one SDP with respect to the other. There has been actually the case noiseless case has a long history because it is related to rigidity theory, and there is this long-standing question of given a graph and a set of distances, is there a unique set of points that realize these distances? So this is a history that actually I know very little about. I think it was settled in 2 dimensions, essentially by Lovash and Yemini and others, and was settled in general dimension only recently. And there is a notion of generic rigidity here that I'm not going to talk about. Okay. So here, what the model that I'm going to look at is this adversarial model. That is, my measurements are far from the actual distance at most by delta. No? And for simplicity, let's say that the range at which I measure things is log n over n to the power 1 over d. Why this funny function? Because this is essentially the first radius at which the graph becomes connected. If the range is much smaller, the graph is multiple component and you cannot position. Okay. So what happens? So this is the theorem that we have. So under this hypothesis, with that probability, okay, this SDP returns an error. Okay, the average error per position is upper bounded by n to the 4 over d times delta. Okay, here there is an h missing. So this is a bit annoying because there is a factor here that diverges with the number of points. So you wonder whether this is the best factor that you can get, at least in the analysis. And yeah, it's not that we are at least within this precision, we did things correctly, in the sense that there exists an adversarial set of measurements and configuration of points such that a set of measurements such that the error is at most of that order. And here the twiggle means that for these slides I'm forgetting log terms. But somebody might be more careful than me. So I'm not only forgetting, but I'm very sloppy, really, any constant log n. Okay, so this was what we were able to do. Actually, it's quite interesting. The upper bound is a lot of things are very related to Markov chain analysis, so analysis of Laplacian on this graph. So a lot of things are related to this, but I will not talk about this. Lower bound, I'll just say one thing about lower bound. What is the worst case configuration? So for a while, we just struggled trying to improve our upper bound because we thought that the lower bound is this. The worst case configuration is this. You have a set of points, And the adversary, what it does is that it blows up by a constant factor all the positions, and then returns you the measurements corresponding to these distances. Okay? And then gives them back to you. And what you do, whatever algorithm you will use, you will reconstruct this position. So you will get an error between the actual positions and the reconstructed position. Now you do the math of computing what is the size that of the error that you get for this kind of noise, adversarial noise, and you get n to the 2 over d times delta. So for a while we tried to push down the upper bound, and we didn't succeed. And we didn't succeed for a reason, is that this is not the worst case configuration. So what is the worst case configuration? It's actually pretty, it's this one, right? The SDP doesn't know what is the dimension in which you are embedding the problem. So when it returns you a gram matrix, it returns a gram matrix in n dimensions, not in 2 dimensions, right? So the adversary, what he will do, he will take your points, and then, okay, this I struggled to do this picture, but he bends you in the 3rd dimension. And now he has this point position bent and computes all these distances, gives these distances back to you. What you will do, the SDP will reconstruct this point position, then you do the singular value decomposition, so you flatten it. You do your math, you compute everything, and you get that the adversary made you make an error that is n to the 4 over d times delta. This has nothing to do. So, of course, there are ways to, once you understand that this is the worst case, there are ways to improve the algorithm. Okay, but I will not talk about it.
Okay, so can you go back to, now that you told us the example, what was this theorem? What upper bound did you get?
It's the same up to this up to polylog factors.
And you won't reveal to us what is the power of law.
I don't know. I don't know. It's unknown. I don't know. Yeah. Shame on me. So conclusion. So there is. Okay, there has been a singular value decomposition for analyzing large matrices is something that is relatively well understood. All of these non-spectral methods, I think that is quite less understood, and it's very interesting. And there is some non-trivial probability that perhaps people can contribute to, and it's still open in the end. And there has been all these papers, but the precise, sharp characterizations are open. There has been some work, and this is very interesting, about other methods. In reality, the data are not of any finite rank. So the right way to think of it is that they are of rank n, so full rank, but somehow you want to discount things that have things that have all the singular values of the same order. And you are trying to reconstruct a matrix. The real structure that you are trying to pull out is something in which there is a few that are singular values that are big, and many that are small. Okay, so what is the correct way of pull out this structure? One has to cook up the right function to be optimized. Okay, so this is related to non-parametric methods. And finally, there is an interesting question that is, even for singular value decomposition, what happens if the matrix is really huge, in the sense that doesn't even fit on a single machine? And what are methods to solve these problems in that case? Okay, so these are interesting research direction, I think. Okay, thanks.
Further questions?
Yeah. For the worst case scenario you just draw that, I think one way to fix that, you can, in SDP, instead of minimizing the trees, you can maximize the trees.
Yeah, there is this idea of maximizing the trace.
Then you will.
But then you have to put a linear constraint. But the point is that you see that the point is that if somebody gave you, I mean, it's not clear that will work, but this is a possible trick. Another trick is that you do the following: if 2 points are not connected by an edge, you still can compute an upper bound on their distance just by taking the shortest path in the graph. So you can put that upper bound in your SDP. And you can, this upper bound is actually pretty good. If there are enough points, it's within 90% correct. So you put also a lower bound in your SDP. So this will be like adding all the edges in your graph, but with some bigger error. So we are actually trying to do the analysis of that right now. But yeah, I mean, once you understand what is the problem, then there are fixes that one can try to.
Then you can go ahead and do standard metric multidimensional scaling.
Yeah, good question. So there is this method that I didn't talk about that is multidimensional scaling. That is exactly what I was saying. Is what you do is that you take you fill your matrix by putting on all the entries that you didn't observe the length of the shortest path. Great, but even if the measurement, what is bad about this method is that even if the measurements are exact, this will not return the exact position, right? Mm-hmm. We'll return something with some error, and actually it's not. So it's like, in my first example, it's like simple singular value decomposition. Singular value decomposition, even if the rank matrix is exactly low rank, and you observe without noise, you will not be able to reconstruct exactly. So there is this extra, that you get from SDP that you don't get with MDS.
Any other questions, comments? Oh, let's thank you very much.